I'll go to the last talk. I think it is online. It is going to be given by Samuel Hunt from the University of Glasgow. And the title is The Temporal Firefighter Problem.
Thank you very much for the introduction. Can you all hear me and see the slides?
Yes, we can see them.
Great, thank you. So this is joint work with my supervisors, Jessica Emwright and Kitty Meeks, both also from the University of Glasgow. And I'm going to be talking about a problem known as firefighter, which has been around. Some of you might know it. It's a problem that's been around since the 90s when it was first suggested by Bert Hartnell. And this deals with process where a fire or some kind of contagion is spreading over a graph, and we want to reason about how we should best contain this contagion by defending vertices of the graph. And I extend this to temporal graphs. So to start off with, I'll just give an example of the classic static firefighter and then go on to explain the fairly natural extension of this to temporal graphs. So at some time zero, a vertex begins burning. This is the root. It's shown here in orange. And then at time one, we get to deploy a firefighter to any non-burned vertex of the graph. So this here is shown in green. And once a vertex is defended or once a vertex is burning, it will stay that way until the process is over. And yeah, until the time ends. So yeah, after we defend this vertex, the fire then spreads to any vertices it's adjacent to. And we repeat, we make another defense. And then you can see here that the fire can no longer spread. We've contained the fire. There's no undefended vertices that the fire is adjacent to. So the process is over. This is phrased as a decision problem where we ask, given a graph and a route at which the fire will start burning, if there's some strategy for defending vertices that can save, so prevent at least k vertices from burning. And this problem is famously very hard. It's hard on trees, it's hard on most graph classes you can think of. There's a few exceptions. There's a list given here, which was there's a few graph classes discovered by Fomin and Hegenes, in which there is actually polynomial time algorithms, and also there's graphs of maximum degree 3 as long as the root has degree 2. But other than these very few classes, in most places this problem is quite hard. I'm going to extend this to temporal graphs. I won't stick around on the definition we're using too much because we've seen this plenty of times today already, but it's the same definition a lot of people have used, where we label the edges with some function lambda, which just assigns sets of integer times at which the edges are active. And yeah, you can view this as a series of snapshots of static graphs with the shared vertex sets. The only other thing to note is I'll denote the lifetime of the graph being the maximum time step by capital lambda. So in temporal firefighter, things work much the same as the static problem, except the fire can only spread down edges that are active. So once again, at time zero, the root begins burning, and then we get to make a defense. And then the fire spreads, but only to vertices to which there is an active edge. And we make another defense. And then you'll notice that actually at this point, the fire can't spread. There's no active edges incident at the fire to non-defended vertices. But the process isn't over yet because the fire could spread again in the future, but we get to just make another defense instantly without the fire spreading. And now truly the fire could never spread again. Let this run forever and the fire's not going to spread anywhere. So the process is over. So in some ways, this making this problem temporal actually makes things easier. It at least doesn't make answering the decision problem easier, but it makes it easier to stop the fire spreading, right? Because if you take a graph and you assign some times to the edges, all you can do is slow down the spread of the fire by doing that. You're not adding any way in which the fire can spread. You're only saying, well, these edges now at some point aren't active, which makes the job easier. But and in this case, we can actually just view static firefighter as a special case of temporal firefighter where all the edges are just active every time, which means that whenever the underlying graph, this being the union of all the snapshots, belongs to a graph class for which static firefighter is NP complete, temporal firefighter will also be on NP. It will also be NP complete on any graph from that class. We quite easily, you can see that the algorithm for static firefighter on graphs of maximum degree 3 with the root being degree 2 works much the same on temporal firefighter. The idea here is that you just, because the root has degree 2, you defend one vertex next to the root and the fire spreads to the other one. And then there are 2 further vertices the fire could spread to. You defend one of them, the fire spreads to the other. So you can restrict the fire to spreading down just one path. And you just find the shortest such path at which you can contain the fire and defend accordingly. However, for most other classes of graph, things are rather more challenging. On the previous slide, I gave this fairly long list of graph classes that there were known polynomial time algorithms for. And unfortunately, temporal firefighter is NP complete when the underlying graph belongs to any of these classes. And that's because temporal firefighter is NP complete on cliques. And the reason for this is that basically you can simulate static firefighter on an arbitrary graph using temporal firefighter on a clique. And you do this by, if there's an observation here that if you say n is the number of vertices in your graph, then the fire has to stop burning by time n-1, because you make one defense per time step. By time n-1, you've defended every vertex other than the root. So the fire definitely can't spread anymore, so the process must be over. So if you take this arbitrary static graph that you want to simulate firefighter on and just assign times to its edges that are active at every time up to n-1, and then add in edges to make the graph a clique, and to those extra edges just assign them any time greater than n-1, then temporal firefighter on the graph constructed in this way will just give the same result as static firefighter on the original input graph. Now, this to me seems a bit like cheating, because I'm claiming this is a clique, but what does that really mean, right? Yes, if you take the union of all the snapshots, you get something that looks like a clique, but I've got a bunch of edges in there that don't affect the spread of the fire at all. So it doesn't seem very clique-like to me. I've just got some edges that I claim are in my graph but actually aren't doing anything. So we then asked, well, maybe just think about this, but we'll just bound the lifetime of the graph. So we'll say that every time, all the time steps have to actually be less than n-1. So every edge at least has the possibility of actually affecting the spread of the fire. But it turns out we can still cheat in much the same way by just taking our input graph and making it a lot bigger by adding a bunch of vertices that are certain to burn instantly. So we can just, so there's no point defending in this set of added vertices. And then we play much the same game, except now, because our graph's way bigger, but we're assigning times in the same manner, the times we are assigning are below n-1. So this, again, less cheaty maybe, is still doesn't really seem that there's anything clique-like going on here, because there's still edges that aren't affecting the spread of the fire. So I think really what this tells us is, as you might expect, looking at the underlying graph and looking at structure there for complexity results doesn't really tell you anything. It happens to work in the very sparse case where you have your underlying graph has maximum degree 3 and a root of degree 2. And I think that's because all the tricks I can play are basically, I can take, with temporal graphs, you can take a very dense graph with lots of edges and make any of the edges you don't want to matter not matter by just cheating and setting the times accordingly. Whereas if the problem is easy because the graph has very low degree, making edges not matter isn't going to make things harder. But on the whole, looking at the underlying structure of the graph doesn't seem too fruitful, which I think is expected. So clearly the thing we should do when looking for complexity results is actually look at the temporal structure. And so we looked for graph parameters that would give us fixed parameter attractability that actually measure something about the temporal structure. So we've also seen this a few times today already, but we say a problem is fixed parameter tractable if we can find some measure of the input such that the time complexity grows arbitrarily large in that measure, but in the size of the input, the complexity only grows polynomially. So we find that temporal firefighter is fixed parameter tractable when we use the graph parameter vertex interval membership width, which I think Hendrik mentioned this parameter in the earlier talk briefly. And this parameter basically captures the idea of counting at each time step the number of vertices that are relevant. What I mean by this, if you look at this example here, this vertex at the center of this star has incident edges active from time 4 to time 8. And what this means is any time before time 4, the fire cannot have reached this central vertex, and any time after time 8, the fire cannot leave that central vertex, which means when we're thinking about firefighter on a graph containing this vertex, we only need to consider that vertex between those times, because we know for sure that before those times and after those times, it's not going to matter. So in particular, the vertex interval membership width measures the maximum size of an entry in a sequence called the vertex interval membership sequence. And this is just a sequence of sets of vertices with a set for each time step. So for each time t, we have a set, and we include a vertex in this set for time t if the active interval, so that being the first time at which that vertex has an incident edge and the last time at which that vertex has an incident edge, contains the time t. So this means for every time step, we have a set of vertices that we need to think about at that time step. So there's a brief example here of this graph has vertex interval membership width 4, and you can see the sets for each time here. And I'll use a little omega to represent the vertex interval membership width. So our FPG algorithm actually uses a slightly related problem, not exactly how I would define temporal firefighter, just because it makes things a little easier to think about. And this is called Temporal Firefighter Reserve. And the idea here is that rather than having to defend one vertex a turn, we can sometimes not defend for a few turns and save up our defenses and do them all at once. So on turn 1, we could not defend anything, and turn 2, we don't defend anything, and then turn 3, we get to defend 3 things all at once. And this doesn't affect the number of vertices you can save at all, because if you imagine, to begin with, any strategy for Temporal Firefighter already is a strategy for Temporal Firefighter Reserve. And to go the other way, every time you skip a defense and save it till later, you can just move that defense back in time and come up with a strategy where you do still only defend 1 vertex per time step. But this makes things easier to think about because it means we can delay all defenses until right before the vertex we're defending would burn. Because we no longer have to, because we can save our defenses up, we no longer have to say, well, 3 vertices are going to burn this time step, which one do we defend now? And we defend some of them earlier. No, we can just defend all those, as long as we save up the budget, we can just defend all those vertices all at once on the turn, right before those vertices would burn. So we dynamically program, and we just compute possible states, every possible state of the Temporal Firefighter process. So we just compute sets of defended vertices, sets of burnt vertices, a budget, and also keep track of the total number of burnt vertices. And in particular, we only need to keep track of the defended vertices that are relevant. So for each time step, we only consider the defended vertices in the corresponding entry in the vertex interval membership sequence for that time step. So the size of these defended vertices and burnt vertices sets is bounded by the vertex interval membership width. So we begin by initializing that there are, right at the start of time, there's only 1 possible state, and that's that there are no defended vertices, the root vertex has burnt, we have a budget of 1, because we can make 1 defense after this happens, and yes, the root vertex has burnt, so the total number of burnt vertices is 1. And then we just, from that, we look at every state in that set, and we just consider every possible defense and just create entries accordingly and just iterate through the time steps, building up these sets of states. And as I said, because we only need to consider relevant burnt and defended vertices, we have that the size of these sets is bounded by the vertex interval membership width. So for each set of states, there can be at most big O of 4 to the omega, where omega is the interval membership width, times omega times the lifetime squared entries. And then for each entry, there's at most 2 to the omega defenses, because the number of possible defenses is just the size of the power set of the entry in the interval membership width sequence. So there's that many defenses to consider, and we have to consider those defenses for every entry for every time step. So we get an overall runtime of 8 to the omega, omega times the lifetime cubed. So this gives us FPT, because here I'm using you can kind of, because of what I said earlier about the lifetime of the graph, you can bound the lifetime of the graph by the size of the graph, because once you reach time n-1, you know certainly that temporal firefighter has to be over. So yeah, this is FP2. So to conclude, restricting the structure of the underlying graph for this kind of problem is not very useful. It kind of tells you nothing. I have this reduction where I claim, look, it's hard on cliques, but what does it mean for the underlying graph to be a clique? But when we actually look at the temporal structure, we get a nice dynamic programming FPT algorithm. So the sort of general future work is, this seems to be an interesting thing to look at. Like, we have a lot of graph problems on static graphs. How can we extend these to temporal graphs, and how might we be able to make use of temporal structure to solve these problems? And more specifically for this problem, we recently looked at, this is a fairly new result which should hopefully get written up and at least put on the archive soon. We think that bounding the number of edges per time step still means that temporal firefighter is hard. In fact, we also considered bounding the interval membership width, which is a very similar parameter to the one I just described, except rather than sets of vertices, you just look at the sets of edges with overlapping active intervals. And yeah, unfortunately, we have a reduction here, which seems that things remain very hard here. In fact, it's a reduction where on a tree where the depth of the tree is 2, and there's only 2 edges active per time step, and in particular, the interval membership width is also 2. So this doesn't seem too hopeful. The only way we could go further from there is the tree does need very high degree on the root. So maybe if we limit the activity of the edges and the maximum degree, we might be able to get somewhere. And something we've not really looked at all yet is the approximability of this problem, because there's quite a lot of known approximations for a static firefighter. So this could be a natural thing to look at. And then there's a few similar related problems that capture other ideas of contagions spreading over graphs, which is quite a, I think, especially in recent times, maybe a useful thing to be modeling. So yeah, there's ideas where it's rather than the adversary, but you become the adversary, actually try and spread something over a graph as fast as possible. And I think all of these extend very nicely to temporal settings. If you're considering something, say, spreading over a population, and you have a contact network and you're using one of these problems to model that, it seems very natural that your contact network people or individuals are only in contact some of the time, rather than just the contact network being static. So I think these are useful to study. Yeah, that's time, I think. That's all I have. Thank you very much.
We have time for a few questions. So do you have any question from the audience or from the online audience?
So have you looked at simple temporal graphs where each edge has only one label?
Yes. So in particular, the reduction I just mentioned for
with the depth to a tree?
Yeah, that is a simple temporal graph.
Okay.
So yeah, hence why things seem so difficult, really. Like I was very surprised by that. I was going in the direction of trying to find, I personally expected that with interval membership width 2 and the temporal graph being simple, I expected it would be easy, but apparently not.
And is that strongly NP hard or weakly? Is there some?
Sorry, I didn't quite catch that.
Is it strongly or weakly NP hard? With that reduction when you're in the case of a tree. Well, I guess there aren't any. There's nothing that you wouldn't encode in unary, so it must be strongly NP hard. Is that right?
Yeah.
Yep.
It is.
I
Thanks.
have a question also. Just came to my mind. If you select to put the firefighters every time at random positions, what is the probability that the fire will stop before reaching everything?
That's a very interesting problem. I'm not very well versed in any kind of randomized probability stuff, although I do work with a lot of people who are. So if you want to get in touch about that, I can probably talk.
Yeah, the algorithm is very simple, but I wonder if it has any effect.
Yeah, I wouldn't know about that. This is very interesting.
Okay.
If someone should do it in practice.
Yes, please.
I also have a question. So if you think about like generalize this problem where so you have like the fire spreading, but then once the fire spread, nothing moves. But you could have like the fire like burn the vertex stopped, and then you have some immunity time, and then you can burn again, and you want to like kill the fire on the ground. You think it's like just like one step after you got the firefighting problem where you just fight the fire and then extinguish what is burning, or is it more intricate?
So are you talking about sort of changing the model so that the fire can sort of stop burning and then burn again at a later point at the same vertex? Yeah. So we've thought about that a little bit. We don't really have any results there yet. I think there's some work in, at least in the static case, where people have looked at changing the model so it's not just things are burnt and defended for all time. So and I think as well, I kind of alluded towards the fact that this is one of the applications of this area is attempting to do epidemiological modeling. So obviously changing the problem in that way, I think makes a lot of sense for that, because people don't remain immune to diseases indefinitely and people don't remain ill from diseases indefinitely. So I think it's a very natural way to take the problem, but we don't have results there yet.
Okay, thanks.
Any other question? Well, if not, let's thank Samuel again. Let's thank all the speakers of this section also.